From the Library of Congress in Washington, D.C.
There's something about a freight train that talks to the very heart of a boy, and to the boy that lives within a man. A freight train fetches treasures from wonderful places and takes them to other places that must be wonderful too, because they're somewhere else. A boy's first geography lesson is a train, because a train says, come with me to New York Central, to Louisville and Nashville, Boston and Maine. One moment, a boy's world is a mixture of Main Street, home, the ballpark, and the schoolhouse. Then the huge engine pulls in. The air is perfumed with diesel smoke, and the big traveling show comes to a stop on the local siding.
It takes an awful long time to stop a freight train. And then the greatest important people in the world get off and have a talk with Mr. Harris. They probably tell him that they can only stay a minute and 27 seconds, and that everything is okay in California and some other places, like Massachusetts.
A freight train drags a string of opportunities to a boy's hometown and asks him to make his choice. Will this boy raise cattle on the western plains? Will he someday be a farmer? There's plenty of land and millions of appetites. Is there a bulldozer in his daydreams? There's a whale of a lot of construction yet to be done in America. Airports and factories, housing and highways. What does a chemical tank car say to this boy? Is chemistry his future?
Ortho, night, rocco, oro, benzene. Wow!
This boy doesn't realize that chemistry is involved in every single industry whose products filled this train, and every other freight train in America pounding through on the main track behind it.
Those engineers are always in a hurry to get going. And their helpers in the caboose are too. Because they have a lot of other places to go and see. Boy, that's the way to live. I wonder what that word means. That orthonitrate, something or other.
A freight train rolls away, but it always leaves behind it some part of its wonder and mystery, like a strange new word in the mind of a boy. My thoughts just naturally slide back to the 1920s. Seems almost like yesterday. Back in the 20s, boys didn't know anything about jet engines or television, of course. And they sure didn't see many tank cars full of orthonitrochlorobenzene running around. They couldn't have pronounced the stuff either. But one thing sure, they certainly would have been curious about it. Just the way they were curious about the things that belonged to their time. The word why was the biggest part of their vocabulary. Why did the blacksmith cook the horseshoe before he hammered on it? If he wanted it hot, why did he dip it in water and cool it off? And if he wanted it cold, why did he put it back in the fire? There wasn't any noticeable labor shortage back in those days either. There was an odd job for every boy. One of the best young chemical engineers I know started out clerking in his dad's grocery store. But he liked chemistry too. He had no way of knowing the chemical industry would someday need both of his talents. It was a golden age for young wizards. Radio was brand new, the miracle of snatching sound right out of the air. Crystal set builders, blacksmith watchers, grocery boys, they're the kids who put the long names on the chemical tank cars you see today, when they got the chance to try. Chemistry in America, even in the days of World War I, was a frontier science. A chemical plant looked about the same as a shirtwaist factory and attracted a lot less attention. The chemist was a pioneer. He worked in crudely equipped laboratories, producing essential compounds known today as the building block chemicals. The sulfa drugs were asleep on a shelf. The magic molds that would someday be called the miracle drugs were not yet under the microscope. But these men were laying the foundation of a great chemical industry in the United States. When the 1930s came along, the boys who carried slingshots in the 20s were old enough for college, still curious about the how and why of things. A lot of them chose chemistry. And they were going to be the dreamers, planners, and managers of a great age. They were finding out from their professors all across the United States what the future held in store for them, how big the dream was.
Chemistry is interested in every aspect of man's world, bounded by the firmament and the thin crust of earth to which he clings. Chemistry is concerned with every basic element of man's survival. The clothing on his back, the food on his table, the roof over his head, and all the many things beneath that roof that enrich his life, increase his comfort, and prolong his stay on earth.
Beyond the campus, the biggest war in history was brewing, and the nation called the brand new bachelors of science to help build the arsenal of democracy. The young chemists delivered. They produced sulfa drugs in quantity, in time to save casualties from becoming fatalities. They put synthetic rubber on war wheels and nylon in parachute packs. They put plastics where critically scarce metal used to be. And finally, they were asked to share leadership in the greatest scientific project in 1940-odd years. The project that made the world stand still and count. 0 minus 15 seconds. 0 minus 10 seconds. 0 minus 5 seconds. When the war ended, the world fell back exhausted, stunned by the violence, but stirring with life, as the sea after a storm. For the young chemists, it was their first opportunity to follow the true purposes of their science, to protect life, improve life, and prolong it. At last, they could work in peace. The nation's industrial skyline parted in the middle to make room for the growing chemical industry. The kids who whooped and hollered at freight trains in the 1920s were now expanding this new industry in plants that no longer resembled warehouses. Now they looked like battleships anchored in concrete. The chemical engineers wrote their shorthand notes in steel against the sky. The writing looked complicated, but the message was clear. From now on, man could look to chemistry to release him from his dependence on fortunate circumstances. The chemists had learned to duplicate natural resources, to extend them, to preserve them where possible, and replace them when necessary.
Most of our achievements begin in the research laboratory. Research is our gamble that we can do something first, or do it better and more economically than it's ever been done before. Sometimes we know before we start what the results will be. But research can be full of surprises. For example, my division of the company assigned a research group to find a special fluid that could be combined with a plastic base to make better shower curtains. The group discussed some possible starting points, and the search began. "2,000 miles from the chemistry lab, a seemingly unrelated research job was in the air. An outstanding aircraft manufacturer was trying to add a new measure of safety to his already reliable airliners. He was searching for a new fluid to put in the main hydraulic systems and the cabin superchargers of his big passenger planes. He specifically wanted a fluid that was fire resistant. In the test lab, his technicians were firing tracer bullets into existing fluids and starting fires. They were dropping all known hydraulic fluids on hot metal manifolds and starting fires. They were forcing these fluids through nozzles and putting an acetylene torch to the spray and starting fires. Fire was what they didn't want, but they were getting it. Back in the chemistry lab, nobody was thinking of hydraulic fluids for airplanes. The men of the research team kept on looking for a new shower curtain material. Their methods would have seemed unreal to those who liked the weird fiction approach to science. No mad geniuses here, staring at the wall with burning eyes. Just normal men, talking, asking, and answering. They stimulated the best of each other's thinking. This kind of product application research is something like looking for four-leaf clovers. First, you have to find a place where clover grows. And after that, you're on your own. If an experiment doesn't go as well as you want it to, you keep on trying. That's what these men did. They kept at it. And one day, they made it happen. A few days later, samples of the new material, now in powder form, were tested on the laboratory scale rolling machines. What came out was a thin sheet of tough plastic, just right for shower curtains. The new plastic passed the standard tests with ease. When it came to the flame test, we knew we had hit on something. 4 strips of plastic from the same general chemical family were put to the torch. Three of them burned under intense heat and were promptly discarded from the test. But the new plastic resisted fire. This fact was duly noted on the progress report. And when the airplane manufacturer asked the chemical company to help find a fire-resistant fluid for his airliners, we had the answer ready. The liquid, intended only for the shower curtain plastic, was given the fire test in the lab of the plane maker. It not only resisted fire, it snuffed out the flaming torch. The chemists built lubricating qualities into the fluid until it extended the life of moving aircraft parts 10 times over. They called it Skydrol hydraulic fluid, and it has flown millions of miles around the world without failure, contributing to the safety and peace of mind of every man who travels the high highway.
Memorandum concerning the forthcoming tour of the phosphorus plant. I recommend that visitors be brought to the plant the night of their arrival for a look at the night shift operation. From a distance, we can show them 6 of the world's largest electric furnaces for producing phosphorus. At the same time, we can show them how we tap a furnace to remove the slag. The following morning, our guests can be brought back to see the day shift taking over. We'll move on over to the mining operation, show them how we get the raw material for phosphorus. We'll explain that the reddish-brown earth we mine contains billions of tiny skeletons of pinpoint-sized animals dead for millions of years, and that these microscopic bones have been leached by groundwater into what we call a matrix of phosphate and lime. Next, we'll look at the matrix going into the washer plant, where the heavy clay is separated from it. At the center plant, we'll just explain that out of the mixing and processing of matrix with coal, coke, and sand in white-hot crucibles, with smoke and cinders and flaming slag, we produce Spitfire phosphorus. Summing up, we'll say that this wild element makes the important phosphates that do the gentle chores in life. Phosphates to make soft drinks and sugar, to help bake the bread, to wash the clothes, to fireproof, yes, fireproof textiles, and improve engine oil, to soften water, and to make jelly. I think you'll agree that there's something a little magical about chemistry. The minute you stop being overwhelmed by the technical side of chemistry, you discover that it's a kind of scientific supermarket in your life. There's barely a minute of your time on Earth that is not in some way made secure and comfortable through chemistry. In many ways, chemistry is the watchdog of our safety. Every time we get into an automobile, we are concerned with a highly important aspect of safety. We take it for granted that we're protected by safety glass. And we are, well protected, because the kids who were curious about crystal sets and horseshoes in the 1920s became curious about plastics in the 1940s. The plastics research men created a material called vinyl butyrol. They rolled it into thin, tough sheets and put it between two slices of glass to make safety sandwiches. Then they put the sandwiches in an autoclave to clarify the plastic and seal the layers of glass in a permanent bond. Each time they make a new sandwich, they put it to the standard tests. First, the drop test with a steel ball weighing half a pound. The ball is taken up to 18 feet. And dropped on the glass. The glass withstands the smashing and passes the same test in temperatures ranging from 0 to 120 degrees. So they give it the hammer test. And rate it according to how much plastic is exposed when they're through smashing it. That is all the proof the glass industry wants. Windshields and door glass are sliding down production lines. The new plastic is the new standard for safety glass in the automobile industry. That's why I say there's scarcely a minute of a person's life that is not in some way made safe and comfortable through chemistry. We take it for granted. We don't give it a second thought.
A good research chemist is a versatile man. Yesterday, he worked on plastics for safety glass and hydraulic fluid for airplanes. Today, he's investigating lumber. The problem? To try and get vanillin, the chemical heart of vanilla flavor, from a tree. We started that one at a modern wood pulp mill, where logs were stripped of bark under high-pressure water nozzles. The peeled logs were fed into huge chipping blades that chewed them down to uniform chip in a matter of seconds. The wood chips eventually became pulp. But the part we wanted was a byproduct called sulfite liquor, a clean, dark brown fluid that used to go down the drain as waste. we knew that this dark brew from the pulp mill contained vanillin. We spent 8 years working on that dark brown brew, and finally it paid off. We produced crystals of vanillin. That's chemistry. A tree falls for one good reason, and chemistry finds another. Something good from almost nothing.
The day the dirty clothes began piling up on the floor of the research lab, I remembered what one of my chemistry profs said about chemistry being concerned with the clothes on a man's back. I wish he could have seen our laundry. Everybody on the staff was invited to bring in their soiled linen and get it washed free of charge. We'd been looking for a new detergent, and we'd found one all right, but it wouldn't lather. Instead of labeling it a mistake, we tested it. We dirtied up thousands of cotton swatches, popped them into fruit jars, and washed them in our laundrometer. The bigger stuff we tubbed in the automatic washing machines. We put strict controls on the whole project. All the wash samples were checked with the photoelectric cell to see how white the whites really were. Our new detergent stayed up at the head of the class. Oh, after a year of this, there wasn't a doctor of philosophy in the lab who couldn't have stepped into the laundry business and made a clean success. We whipped up a small ocean of soap suds, and the evidence showed that a lot of suds in an automatic washing machine does not necessarily guarantee the best wash job. Large quantities of suds only cushion the clothes against a thorough cleansing action. Well, once we knew that, we decided to give our new product the all-out treatment. We called for another mountain of dirty clothes for the laundry with a big overhead and no revenue. For another 6 months, there were 5 Mondays in every week. No buttons replaced. No ironing done on the premises. We guarantee only that all clothes will be washed in a new way and handed back whiter than the customer's ever seen them. Hours or 9 to 5. At the end of the line, 18 months from the beginning, we had our almost detergent ready. We called it Sterox. And I think it proves that chemistry is concerned with a good many aspects of man's daily struggle, right down to the clean shirt on his back.
It was a silkworm that gave Professor Robert Hooke his big idea. Way back in the 17th century, he predicted that man might find a way to beat the silkworm at his own game. Man did find a way to beat the silkworm, not in making silk, but certainly in creating fibers. It's really very simple.
You start with a partial oxidation of methane to acetylene, CH4 to C2H2. Thermodynamically, you'd expect CO2 and water when CH4 is reacted with pure O2, but in this controlled reaction, you get C2H2 and CO and hydrogen, actually creating triple bonds between the carbon atoms. Then with the HCN from ammonia, the two gases link up in the reactors over a catalyst.
Get it? Eventually, we created a liquid called acrylonitrile. But that's only half the story. Some 14 more steps are involved before acrylonitrile becomes something to wear. Liquid acrylonitrile becomes an artificial glutinous composition, spin dope. The dope is forced through a spinneret and on into a chemical solution where the strands congeal. The wet white ropes of acrylan fiber are dried as they move out of the coagulation bath and pass under and over a series of rollers. The moist flat bands of fiber are now cut, and after further drying, the fluffing process begins. The material is then baled for shipping to the textile industry, which has joined forces with the chemical industry and is testing and weaving the new fiber. Acrylonitrile, a chemical, leads to acrylan, a fiber. And the fiber leads to fabrics worn everywhere by Americans who take for granted the textile and chemical ingenuity which created them.
After 30 years of science reporting, I can't get too excited about a press conference. But this one had a special ring to it that attracted all the first-string writers in the field. The invitation promised us a preview of a basic new discovery in home gardening and agriculture. After coffee, everybody settled down, and the chemists put in an official appearance. There certainly weren't any props on stage to remind anybody of chemistry. I spotted a few lab dishes, some old glassware, a cake beater, and some samples of dirt. Then we heard the story. A lot of you know the story by now. The chemists took the wraps off a new compound they called Trillium soil conditioner. They said it was their first success in bringing worn-out dirt back to good soil structure. They passed around some samples of their Trillium soil conditioner, along with some little jars of what they called the meanest clay soil they could find, and enough water to make a mud pie out of each jar. They asked us to roll our own and see for ourselves how Trillium worked. For the next few minutes, we had a farm bureau running in the middle of the city. We all went back to the soil and learned something. They showed us a light, powdery material. They said that when this powder is mixed thoroughly into soil that has been broken down into loose particles, the soil will retain this desirable structure. They told us about some encouraging results when they used the compound on heavy clay soils that get brick hard in summer and turn to glue in the rainy season. I put my oar in and gave it a try. It worked for us, and it worked for the fellows in the lab coats. Trillium made it possible to convert mud into little crumbles, the kind of soil structure nature intended, because it allows plants to drink, breathe, and take nourishment, and thus grow at their maximum rate. The soil sample that wasn't treated with Trillium was plain, unmanageable mud. Finally, our hosts showed us some plants grown in treated and untreated soil and let us draw our own conclusions. They apologized for not being able to bring the whole greenhouse indoors, but the plants they showed us had obviously developed healthier roots in conditioned soil. And that was the modest way they told the story. No claims that they were going to make the desert bloom overnight. They stuck to the minimum facts. The minute I had the facts in my teeth, my thoughts switched over to the men behind them. I thought about some of the great things that the chemists had delivered in the few short years since the First World War. The life-saving antibiotics, the huge family of plastics, synthetic rubber, synthetic fibers. I found myself wishing I could be on hand to write the stories about the better things to come. But I had a question. Where would chemistry find the technical manpower to crack the bigger tasks ahead?
Here is the technical manpower to crack the bigger tasks. Here they are, the dreamers, planners, and managers of a greater era of chemistry than ours. They're busy with other things right now. They're busy being young, chasing tadpoles. They're testing their inherited freedom to explore, to measure the world about them. Curiosity, alertness of mind, and a sense of adventure are their qualifications for the job. These are the ones who will take over the unfinished crusades of today's scientists. These boys may be asked to cancel cancer, beat the common cold, conquer heart disease, harness atomic energy for peace. They will inherit the chemical industry's role of service to all humanity through industries that serve humanity. Industries we know today and others we've never heard of because they haven't yet been born. They will be created by today's boy and tomorrow's man when he makes a decision for chemistry.
This has been a presentation of the Library of Congress. Visit us at loc.gov.